So we are on live now, sir. Sir, session is to you, sir, Kumar, sir.
A very good morning to each one of you. I am delighted to invite each one of you to the day 6 of the AICT sponsored webinar. And today's speaker is Dr. Arvind Bansal, sir. And as I don't think I need to introduce sir to most of you. Sir is a well-known and eminent personality in the field of pharmaceutics. Sir has vast experience in industry and academically is doing an excellent job. And his regards and his publications and his citations and his patents, everything, when I look at it, it reminds me of the records of Sachin Tendulkar in cricket. So, and Sir's work is cited in almost 8,000 citations, excellent patents record and publications. I don't know how many presentations he has given so far, and I'm sure he's tried giving presentation on and again. So with this note, I think Sir has suggested that instead of presenting, to present his talk in video form. I can understand, sir, why you suggested that. Sir is available to each one of you. So if you have any questions, you can type your questions in chat box, and sir is available throughout the session, and sir will answer each of your queries at the end. So on this note, on behalf of the Vishnu Education Society and faculty of Sri Vishnu College of Pharmacy, I wholeheartedly welcome each one of you to this session. And I personally thank Arvind Badra sir for accepting our invitation in spite of his sir's busy schedule. We ideally wanted this program to start with sir, but sir could make it today. And I really thank you, sir, for making your time and trying to share your rich knowledge and experience with all the faculty around the country. I sincerely pray God that God gives you more energy than what you are now to enlighten this the young blood of the pharmacy and enrich this profession in India, and your contributions is throughout the world. Your students are performing excellently throughout the world, and we wish that this saga will continue for longer period. So with this note, I will pass on this for the next steps to Venkateswar Raju garu.
Sorry for the small technical lag. Within 2 minutes, our moderator will join us.
Sri Vishnu College of Pharmacy is very reputed in the Bhimbaram area, and actually we cater to the needs of industry in both R&D and manufacturing. It is the first private pharmacy college affiliated to Andhra University, and SVCP was the first pharmacy college accredited by NAC and NBA. The institution offers B.Pharm, M.Pharm, PharmaD, and M.Pharm in 6 specializations, and as well as PhD courses. At SVCP, we strive to keep abreast with the latest advanced knowledge and skills for all students and faculty. We are organizing a short-term training program from 22 to 27th of February of this year. And I want to give a brief introduction about our reputed speaker, Dr. A.K. Bansal Garu. And Dr. A.K. Bansal sir is currently professor and HOD of pharmaceutics at Naipur, Mohali. చూడండి మళ్ళా he earned his pharmaceutics and PhD from University of Delhi. And Dr. A.K. Bansal sir worked as senior scientist and group leader in JK Pharmaceuticals and ran Ranbaxy research labs for 8 years. And he conceptualized formulation strategies, developed and transferred technology to the production shop floor for new chemical entities and generic products. Dr. Bansal Garu joined Naipur in 2000 and developed expertise in the areas of pre-formulation and formulation development, encompassing characterization and stabilization of amorphous form, polymorphism, pseudo-polymorphism, particle engineering, screening salt forms, improvement of oral bioavailability and lyophilization. His research group works with the mission statement developing science-based industrially viable pharmaceutical technologies and works closely with pharmaceutical industry to create opportunities for commercial exploitation of the products. Dr. Bansal Garu was conferred prestigious fellow of American Association of Pharmaceutical Sciences in 2016. He is the only Indian working in India to be awarded this fellow status of American Association of Pharmaceutical Sciences. And sir won prestigious awards like AAIPS Distinguished Educator and Researcher Award, Innocentive Award, OPPI Award, IPA ACG SciTech Innovation Award for 2018 for Best Innovative Development of Solid Dosage Forms. And Dr. Bansal sir's research group has completed more than 550 industry-sponsored projects, granted 11 patents, filed 27 patents, published 170 research articles, and 27 review articles. Dr. Bansal has total citations of 8,011 with H index of 47 in Google Scholar. He is editorial board member of Journal of Excipients and Food Chemicals, Development Research and Pharmaceutics. He is also advisor to the editorial board of Journal of Pharmaceutical Science and Modular Pharmaceutics. And recently his lab has outlicensed a platform technology on nanocrystalline solid dosage, solid dispersions, that is nano cry SP. That's all from my side, sir. And I'm handing over to our director, Sri Kumar Nemmani Garu.
Sir, would you like to say any few words before starting the video?
Yes, so thank you very much for first inviting me to this program, and I am really happy to be part of this. And as Dr. Raju was mentioning, he requested me to be the speaker on the inaugural day, but unfortunately there was a clash because there was another webinar that was organized by Punjab University Chandigarh on the same day where I had a presentation. Nonetheless, I am happy that I am able to get connected to all of you. I saw the facilities and the video of Vishnu College of Pharmacy. It was really impressive, and the way the education and research are being tackled seems very impressive. It would be wonderful in future to personally be able to visit the place. This time, because of the ongoing constraints, we are not able to meet personally. So with that, I wish all the best to the organizers and thank them for including me as part of this event. I would request all the participants to be interactive, and if you have any questions related to this talk or maybe some other topic, feel free to put your queries in the chat box. I will try to answer them to the best of my abilities. Even after the talk, if you have some additional clarifications, my email address would be there at the end of the presentation, and you can write to me, and I will try to answer your query through the email as well. So thank you very much again to the organizer. I had deliberately sent a recorded version of my talk so that there are no technical problems during the connectivity and other issues. So over to the organizers for the next step. Thank you very much.
Yeah, thanks a lot, sir. We will be more than delighted if you can make your time and personally visit this campus and guide us through the path. Yeah. So with this, Barbara, we can go ahead to start the presentation.
Yes.
Hello, everyone. I'm going to talk to you today about a topic entitled co-crystals as novel solid form for pharmaceutical development. If we have chosen the co-crystal as the solid form for development, what are the challenges that are involved? First, in identifying the most optimal co-crystal candidate, and then subsequently conversion of the co-crystal to a final drug product like a tablet or a capsule or any other dosage form. During the drug discovery stage, as we all know, the pharmaceutical scientists are trying to optimize various properties like potency of the molecule, its selectivity, pharmacokinetic properties, and the material properties. By the material properties, we mean some of the important physicochemical properties like aqueous solubility, intestinal permeability, stability, compactability, and processability. We have the choice of picking up from different solid forms the most suitable one for our pharmaceutical development. Salt forms, as we know, can only be used for the ionizable drug molecules. Crystalline form can be used, amorphous form can be used. Another new area for the selection of the solid form has been opened up by the field of co-crystals. The co-crystals can be developed for non-ionizable molecules, and they can provide us significant solubility benefit while maintaining a reasonable level of physical as well as chemical stability. In today's talk, we will try to understand that if we have generated a number of co-crystal candidates for further development, what is going to be the criteria for choosing the most optimal co-crystal candidate, and the challenges that are involved in its subsequent conversion into a solid dosage form. This is going to be the flow of the presentation. We'll briefly talk about different solid forms of the API. What are the triggers that encourage research in the area of co-crystals? Strategy for selection of co-crystal based on the pre-formulation studies. And we will take an example here or a case study to exemplify this. The formulation development using the co-crystal, and finally we'll try to draw some important conclusions. This picture shows the significance of solid form in pharmaceutical development. Solid form can influence properties like solubility, dissolution rate, stability, both chemical as well as physical, hygroscopicity, mechanical properties like flow and compactability, and overall processability of API into the finished dosage form. An ideal solid form should possess all these properties, and they overlap in this zone, which is called as the sweet spot. This is the zone which has the optimized properties for developability, and our emphasis during the selection of the co-crystal candidate, or for that matter any other solid form, should be to pick up a form which provides us a balance of all these properties that are important for the finished dosage form. At the molecular level, the solid form of the API can be classified broadly into two categories: crystalline and amorphous. Crystalline solids could be multi-component, or they can be single component or multi-component. In multi-component, we have hydrates and solvents, salt forms, and co-crystals. Our emphasis today is going to be on co-crystals. Co-crystals can further exist either as anhydrous non-solvated co-crystals and their polymorphs, hydrated solvated co-crystals and their polymorphs, co-crystals of salts and their polymorphs, solvates and hydrates. On the other side, in comparison to the crystalline form, we can also use the amorphous form. But today's talk is going to focus on the area of co-crystals. Co-crystal has been defined by the scientific community as solids that are crystalline, single-phase materials composed of two or more different molecular and or ionic compounds, generally in a stoichiometric ratio, which are neither solvates nor simple salts. US FDA also defines the co-crystal on pretty much the similar line, except for the fact that they mention that they exist in a defined stoichiometric ratio within the same crystal lattice that are associated by non-ionic and non-covalent bond, which means the molecules in the crystal lattice are held together by non-ionic and non-covalent bond. And this is what differentiates from the salt forms. Here is an example of a co-crystal, carbamazepine and succinic acid system. Carbamazepine is the API and succinic acid is the coformer. In the crystal lattice, we can see there is participation of both the API and the coformer. Obviously, we have a large number of co-crystals that have been reported in the literature for many APIs now. Co-crystals differ from simple salts, solvates, and other solid form, and this picture tries to highlight that aspect. The key differences in co-crystals and the other solid forms are: it is a multi-component system, unlike the polymorphs. Unlike the salt, there is no complete transfer of proton involved in the case of co-crystals, and its synthesis does not require presence of the ionizable functional moiety. Co-crystals have definite stoichiometry, unlike the solvates and the hydrates. Second component in the co-crystal, that is the coformer, is non-volatile in nature, unlike the salts and the hydrates. This table shows the comparative overview of co-crystals with other solid forms in respect of various parameters like solubility, dissolution rate, physical stability, chemical stability, compaction properties, hygroscopicity, and the challenges during the scale-up of the process. In the case of polymorphs, there is a 2 to 3 times improvement in solubility that is possible, while in the case of amorphous, it is 4 to 14 times. Salt forms can give 2 to 1000 times improvement in the solubility. Co-crystals can give an improvement in solubility of 4 to 20 times. In terms of the solubility advantage, they are comparable to the amorphous form, but additionally they have physical stability which is much better than the amorphous form, since amorphous form is the high energy form and has a tendency to convert back to the crystalline form. All the solid forms, since they improve the solubility, will also enhance the dissolution rate. In terms of the physical stability, co-crystal physical stability may be challenging, while the amorphous form is always challenging because it is the metastable form. Chemical stability for polymorphs gives us low to medium risk. For amorphous, it is high risk. Here it is low risk, and in the case of co-crystals, it may be challenging. Similarly, for other properties, we have compared the various aspects of the polymorphs, amorphous form, salt form, and the co-crystals. What comes out from this table is that although most of the time we are trying to optimize on one of the biopharmaceutical property like the solubility, the other aspects of the solid form may not be encouraging for conversion it into the final drug product. So if we have to choose the optimal solid form like a co-crystal for the further development, we have to look at all these properties simultaneously and pick up one co-crystal candidate which provides us optimal properties in terms of all these parameters. We cannot simply look at one of the property and compromise on all other, because all other properties can also affect the safety and efficacy of the drug product. The interest in the area of co-crystals is increasing day by day. And we can see in year 2015, there were 660 publications and 297 patents which were filed in the area of co-crystals. Amongst the patients, 80% of the patents were filed by the pharmaceutical industry, while 20% were filed by the academic institutions like universities. This clearly shows that there is a lot of interest in the industry for converting the APIs into co-crystals and then using it for conversion to the final dosage form. We now come over to the important part of our lecture today. Here we'll talk about a pre-formulation guided strategy for selection of the co-crystal candidate for drug product development. We are going to use a pre-formulation flowchart so that from various co-crystal candidates, we can pick up the most important one. This will also help us in understanding what pre-formulation properties are important when we select a co-crystal candidate. This is the flow diagram which we published as part of a review article that was published in Journal of pharmaceutical sciences. If we have to pick up the co-crystal candidate, the first thing that we need to see is the safety of the co-former. The co-former that has been used for creation of the co-crystal should not be unsafe to use in a pharmaceutical product. Also, the weight contribution of the co-former to the overall co-crystal should be within limits, because otherwise it will be difficult to convert the co-crystal into a final drug product, especially for high dose drugs. The first most important aspect that we need to evaluate is that of the solubility, and within that we will also look at the eutectic constant determination, because this tells us that what is going to be the duration of the solubility advantage during the dissolution stage. pH solubility profile, solubility in biorelevant media, phase transformation profile are all important components of the solubility studies. Thereafter, we should look at the dissolution, intestinal permeability, physical and chemical stability, solution state and photostability, and the hygroscopicity of the co-crystal candidates. Thereafter, you need to ask a question: are these critical parameters satisfied by the co-crystal candidate? If the answer to this is yes, then you can move over to the next stage. If the answer to this is no, you will have to go back and choose other co-crystal candidates. Thereafter, we evaluate other properties like polymorphic screening of the co-crystal candidates, the mechanical properties, the compatibility of the co-crystal with the excipient that are going to be used in the formulation, what is the microenvironment pH of the co-crystal, and what is going to be the impact of this microenvironment pH both on the solubility as well as the stability of the drug product. If these properties, which we call as the additional pre-formulation studies, are also satisfied, then we ask another question: are above parameters satisfied? And if the answer is yes, then we will select the co-crystal candidate for further product development. But if the answer to this is no, then we can have two possibilities. Can we use rational formulation development and container closure system or process design to mitigate the challenges that have been identified? If that is possible, then we'll use those strategies to develop the final product. But if these seem to be inadequate to address the challenges, we'll have to go back to the selection of the optimal co-crystal candidate. And obviously, then again, we'll have to look at the critical pre-formulation studies and additional pre-formulation studies for the new candidates that have been selected. So this is a flow chart, or you can say a decision tree that can be used for choosing the best co-crystal candidate from amongst the number of co-crystal candidates that are generated due to the screening of the co-crystals. As you must have always seen that when we do the screening of the co-crystal, we end up with a number of co-crystal candidates. But out of them, which one is going to be the most suitable for formulation development needs to be assessed on a scientific basis. We now move over to a case study wherein we will take up rivaroxaban as the drug candidate and talk about co-crystal based drug product for improving the biopharmaceutical performance of rivaroxaban. Rivaroxaban is a drug candidate which has solubility and dissolution rate limited oral bioavailability. These are the calculations of the deabsorbable and the time of dissolution, which proves that for the 20 milligram dose, solubility and dissolution rate are the limiting factors for oral absorption. The innovator for rivaroxaban has addressed this issue through hydrophilization of the micronized form of rivaroxaban using fluidized bed granulation for the 10 milligram strength. But unfortunately, using this approach, the innovator could not solve the problem of poor bioavailability of the 20 milligram strength, which is the higher strength that is also available. The required value of solubility to improve the bioavailability of 20 milligram dose was calculated as 11 micrograms per ml, while the current solubility of rivaroxaban is about 7 to 8 micrograms per ml. So we are looking at doubling the aqueous solubility of rivaroxaban, so that the bioavailability of the higher strength, that is 20 milligrams, can also be optimized. As per the decision tree, we proceeded with the experimental evaluation. The first aspect that was assessed was the safety of the coformer. 3 coformers were subsequently chosen, as we'll see in the next slide. The malonic acid, oxalic acid dihydrate, and 4-HBA. And these were then evaluated in terms of their quantity that is going to be present in 20 milligram strength of rivaroxaban. And then we evaluated whether they are within the limits that are existing in the approved products or in certain other guidelines of the regulatory agencies. As is very clear, for malonic acid, the quantity present in the co-crystal for 20 milligram strength would be 7.5 milligram, whereas 80.1 milligram has already been approved in other products. Similarly, for oxalic acid, it would be 11 milligram, and for 4-HBA, it is going to be 19.3 milligrams. So all these were within the range as approved by the regulatory agencies previously. So the safety of the coformer is not going to be an issue. This was the screening protocol that was used for the selection of the coformers. We started with 28 coformers, and while choosing this, we adopted the delta PK rule, which says that it should be the difference of delta PK should be less than 0 for co-crystal formation. And additionally, synthon approach was adopted, and the synthon structure that were identified for formation of the co-crystal with rivaroxaban were oxazolidinone, aminomorpholidone, and carboxamide. Thermal behavior of the binary mixtures of the coformers with the API was assessed using the DSC at different heating rates, and this was the decision tree that was adopted to choose the coformer. And if a co-crystal was formed, that coformer was chosen and taken forward. But if the formation of rejected, we did not take that coformer further. And as I already told you, these were the 3 coformers that were selected: malonic acid, oxalic acid dihydrate, and 4-hydroxybenzoic acid. We then went ahead with assessing the essential properties of the pre-formulation profiling, and we identified solubility, dissolution, permeability, stability, and hygroscopicity as the essential properties. Solubility was the primary objective for which we were creating the co-crystals, hence it had to be evaluated very, very critically. And once we change the solubility, we must also identify its effect on dissolution, permeability, stability, and hygroscopicity. And it should not happen that in the attempt to improve the solubility, we are compromising on some of the other properties, because that is going to overall affect the safety and efficacy of the final drug product. The solubility of the co-crystals were evaluated in biorelevant media, that is the fasted and the fed medium. So in this particular bar chart, we have shown the values of solubility that were obtained. So this is the solubility that was obtained by rivaroxaban in the fasted medium and in the fed medium. This is with the malonic acid co-crystal, this is with the oxalic acid, and this is with 4-HBA. As you can see, 4-HBA did not lead to any significant improvement in the solubility. Hence, it would not be an ideal candidate for taking further. However, we kept on evaluating it for other parameters as well. And from this, it is apparent that the malonic acid is giving us the highest water solubility, and hence could be a probable candidate for further development. However, we must ensure that in an attempt to improve the solubility, properties like hygroscopicity are not being compromised. So in the subsequent slides, we will evaluate the other pre-formulation parameters of these co-crystal candidates. The pH solubility profile of the malonic acid and oxalic acid co-crystals were evaluated. And a very important aspect that came out of this particular study was the phase transformation time, which was more than 4 hours for the malonic acid co-crystal, but it was only 20 minutes for the oxalic acid. This means that the solubility advantage that is going to be obtained from the malonic acid is going to be like a spring parachute effect, and the solubility is going to be maintained at a higher supersaturated level for biopharmaceutically relevant time frames. While in the case of the oxalic acid, the higher solubility that was obtained falls back to the lower solubility very, very quickly, and this is called as a spring effect. The dissolution studies were carried out, and in this also the rank ordering was that rivaroxaban had the least dissolution rate, while the malonic acid co-crystal has the highest dissolution rate. The studies were carried out using a dissolution medium which had a zinc index of 0.45, so that we were able to discriminate the dissolution profile from the various co-crystal candidates. The permeability of the rivaroxaban across CACO2 cell lines was also evaluated, so that we could assess how the coformer affected the intestinal permeability. It came out from the study on the rivaroxaban alone that it has a significant PGP efflux parameter, as the ratio of apical to basolateral and basolateral to apical was found to be 1.88. For a compound with a efflux ratio of 1.5 to 2, a positive effect of the inhibitor indicates the implication of the efflux transporter. This means that rivaroxaban is a substrate for the PGP efflux transporter. Then we compared all the co-crystals and their physical mixtures, and we found that there was no significant difference in the apical to basolateral or basolateral to apical permeability of the co-crystal candidates, which means there was no impact of the co-crystallization of the on the permeability of rivaroxaban. The solid state stability and the effect of microenvironment pH was then assessed. There was no significant degradation in all the samples in the solid state after 1 month at 40 degrees Celsius, 75% RH in the closed and moist conditions. No significant degradation in all the samples in solid state when they were stored at 3 months at 40 degrees Celsius and 75% RH in open and dry condition. However, in the presence of a basic stressor, that is sodium carbonate, the rivaroxaban 4-HBA co-crystal showed a yellow discoloration with 50% reduction in the assay of 4-HBA. However, there was no evidence of degradation of the rivaroxaban. Now, this leads to a very interesting scenario that although the rivaroxaban was not degrading, the coformer was degrading in one of the conditions. And if the coformer degrades, obviously there is going to be the disturbance of the crystal lattice, because the original co-crystal was formed with 4-HBA, while during the stability it has degraded into some other compound. The hygroscopicity studies were carried out for all the co-crystal candidates using dynamic vapor sorption technique. The 4-HBA co-crystal only showed 0.03 weight gain, which is shown by this red colored line, and this black color line, which is almost overlapping, is for the rivaroxaban. This blue colored line is for the malonic acid co-crystal, wherein you see a significant water uptake has been shown by the sample, especially at higher RH values. On this axis, you have the relative humidity values, and this green color profile is for the co-crystal with the oxalic acid, which shows a steep weight loss of 8.8% at RH values below 20% owing to the loss of the water molecule from the co-crystal hydrate structure. The co-crystal that was obtained with oxalic acid in fact was a hydrate form, and when you store it below the 20% RH, it used to show a steep loss of 8.8%. So the rank ordering of the co-crystal candidates in terms of their hygroscopicity was that malonic acid co-crystal was the most hygroscopic one, followed by oxalic acid, 4-HPA, and rivaroxaban, which was almost equal to the 4-HPA. 39 times higher water absorption was exhibited by rivaroxaban malonic acid co-crystal as compared to the neat API, which can be a cause of concern because hygroscopicity can complicate the processing of the co-crystal into the final dosage form. These are the separate absorption and desorption profile that have been shown. So this is malonic acid alone. The red one is for the co-crystal and the black one is for the rivaroxaban. We in fact then went ahead to understand the molecular basis for water absorption behavior of rivaroxaban malonic acid co-crystal, since it was showing 39 times higher water absorption as compared to the pure API. We adopted a crystallographic based approach to understand the molecular behavior, wherein the first was to identify the surface groups that are exposed on various solid forms that were tested. This is the crystal structure of rivaroxaban, which was picked up from the literature. This one is the arrangement of the molecules in the co-crystal with the malonic acid. In the case of rivaroxaban, we have anti-parallel arrangement of two rivaroxaban molecules interacting through a bilateral NHO hydrogen bonding to form a dimer in AB-AB fashion. And these were the characteristics that were observed in the case of the co-crystal. The next study was the phase indexation study, which is done using a single crystal XRD machine after generating a single crystal. And this was done for all the three samples, rivaroxaban, pure malonic acid, and their co-crystal. We generated very useful information through this particular exercise, and we identified the crystallographic planes or the facets in the each sample. What was the relative contribution of these facets to the surface groups that were exposed on these facets, and what was the nature of these surface functional groups. Were they hydrophobic in nature? HPHO denotes hydrophobicity, while HPHI stands for hydrophilic groups. And this was done for rivaroxaban, malonic acid, and riv-mal co-crystal. We also identified the groups that were exposed on the surface using the Mercury software and looking at their crystallographic information file. What are the groups that are exposed on the surfaces of the samples? So this is for rivaroxaban, this is for malonic acid, and this is for the co-crystal. The third step was recognizing the nature of the chemical groups that are exposed on the surface, whether they are hydrophilic or hydrophobic. Because if the groups are more hydrophilic in nature, their interaction with water is going to be much higher as compared to the hydrophobic groups. This was done using the computer software, wherein we are able to see the relative hydrophilicity and hydrophobicity of the various groups that are present in a chemical structure. So we did it for rivaroxaban. The blue colored zones show the groups which are relatively hydrophilic, and the brown ones are the groups which are hydrophobic in nature. So these are the hydrophobic groups of rivaroxaban, while these are the groups which are relatively hydrophilic in nature. We calculated the molecular lipophilic potential using the in silico method, and this was the malonic acid molecule. As you can see here, most of the molecule is hydrophilic in nature, as it is blue colored throughout the molecular structure. Then we calculated the relative contribution of hydrophilic, hydrophobic, and the combination of both to the facets. And we came up with this interesting observation. In the case of the malonic acid, this is the contribution from the hydrophilic groups, while for rivaroxaban, this is the contribution. So majority of the contribution is coming from the hydrophobic groups. While there is nothing which is completely hydrophilic, this zone indicates the facets which have both hydrophilic as well as hydrophobic groups. While in the case of the co-crystal, we can see that the hydrophobic groups have reduced from 65.2 to 57.9, while the combination of hydrophilic and hydrophobic groups had increased from 34.8 to 42.1. This could be one of the reasons for the higher hygroscopicity of the co-crystal as compared to the rivaroxaban. So we concluded that the enhanced hydrophilic plus hydrophobic contribution from 34.8 to 42.1 and reduced hydrophobic contribution from 65.2 to 57.9% could be one of the contributors to the enhanced hygroscopicity behavior of the malonic acid co-crystal. However, the difference in the hygroscopicity of rivaroxaban versus the co-crystal was 39 times. And the values that we obtained in the previous case, these are only marginally different between rivaroxaban and the malonic acid co-crystal. So from 65, it is going to 57, and from 34, it is going to 42. So this does not explain in completeness the reason or the molecular reason for the higher hygroscopicity of the co-crystal with the malonic acid. We then went on to understand that the strength of the hydrogen bond or the strength of the interaction between the hydrophilic groups in the co-crystal and water could be an additional parameter that is contributing to the increased hygroscopicity profile. This was studied using the DFT calculation, which is the density function tool, and the hydrogen bonding strength was assessed by calculating the interaction energy between the various molecules and water. In the case of rivaroxaban, the interaction with water is associated with an energy of minus 5.1, while for the malonic acid, the interaction with water at this particular COOH group has a much stronger interaction because it has a lower energy of minus 10.2 kilocalories per mole. Similarly, the interaction of malonic acid with water at this position, that is the carbonyl position, also comes up with a stronger interaction with respect to the rivaroxaban and water interaction. So presence of surface chemical groups that have strong hydrogen bonding interaction with water molecules favors the water sorption tendency of crystalline solid as compared to those with weak hydrogen bonding interactions. So what came up from this study was that the amount of water sorbed by the co-crystal is governed by the surface molecular environment and additionally by the strength of the hydrogen bonding between the surface groups that are exposed and the water molecules. So this is the entire study in a nutshell, that we first evaluated the nature of the facet in terms of the hydrophilicity or the hydrophobicity. What is the relative contribution of these to each facet, and what is the strength of the hydrogen bonding interaction between the groups that were exposed on the facets and the water. This work has been published in Molecular Pharmaceutics. Then we went ahead to evaluate the other desirable properties in the pre-formulation study, which included the polymorph screening, mechanical properties, microenvironment pH studies, and the compatibility studies with the excipients. There were no polymorphic forms obtained for the co-crystal with 4-HPA and with malonic acid. The co-crystal with oxalic acid exists as a tetrahydrate form. Anhydrous form of oxalic acid co-crystal could be formed by storing the co-crystal at a RH value less than 20%, which was very obvious and could be seen in the DVS studies that we discussed earlier. However, at the ambient humidity, the anhydrous form gets converted into the hydrate form. The mechanical properties in terms of the tabletability were evaluated. This is a low critical pre-formulation parameter for low dose drug like rivaroxaban, because the dose that we were working on is only 20 milligrams. Nonetheless, we evaluated their compactability profile, and we found that the co-crystal with malonic acid has a reasonably good tabletability, and it gives us the value which is higher than the 2 megapascal. So this is the tensile strength which is optimally required to form a good quality tablet, and we were getting a value which was higher than this. The microenvironment pH studies were carried out because they can affect both the solubility behavior as well as the stability behavior of a compound. A thin saturated layer of water is formed at dissolving surface of the solid particle, and this represents the microenvironment, and the pH at this region is called as the microenvironment pH. Rivaroxaban is a non-ionizable drug and has same microenvironment and bulk pH. So since it is a non-ionizable drug, hence the effect of microenvironment pH was not observed in solubility and the stability studies. So this again came out to be a non-critical pre-formulation parameter for rivaroxaban co-crystals. Subsequently, the compatibility studies of the co-crystal with the excipients need to be carried out, because you are going to use certain excipients for the development of the solid dosage form, which was a tablet in this particular case. We adopted a very conservative strategy here, and we used the same set of excipients as were used by the innovator in the original rivaroxaban drug product that is marketed in the international market. Because of this, the co-crystal excipient compatibility was not carried out with the co-crystal candidate. However, this should not be viewed as a general statement, because sometimes the excipients that are compatible with the drug may not be compatible with co-crystals, because there is likely interaction between the co-former and the co-crystal and the excipient. What comes out of this is that in the case of co-crystals, the compatibility has to be assessed not only with the API but with the excipient as well. We then adopted a weighted criteria matrix based on lean sigma approach to identify the best co-crystal candidate. These were the critical parameters that were identified: solubility, stability, hygroscopicity, permeability, and a weightage was allotted to these parameters. Solubility was given a weightage of 40, stability 30, hygroscopicity 20, permeability 10, and the total of these would be 100. And based on this, a net score for the 3 co-crystal candidates was calculated. We ended up with a net score of 480 for the malonic acid co-crystal, while it was 400 and 280 for oxalic acid and 4-HPA co-crystal. And the rank ordering of these co-crystal candidates with respect to their optimum nature for further dosage form developed was: the first rank was obtained by malonic acid, the second one by oxalic acid co-crystal, and the third one with 4-HPA co-crystal. based on this, we can conclude that the malonic acid co-crystal was the best one for carrying out the further development into a solid dosage form. And we then developed a prototype formulation for the co-crystal with malonic acid. We developed prototypes using the excipient that are shown here. The formulation was a tablet. The tooling was 6 millimeter convex tablet tooling. Process was a direct compression process. These were the in-process quality control parameters. The target DT was comparable to the innovator, that is 4 to 5 minutes, and the compression was carried out using a rotary tablet press. These are the quality control parameters that were obtained for these prototypes. So as you can see, the hardness was well within the acceptable ranges. Disintegration type was slightly higher in this case and in this case, while it was optimal in this particular case because we wanted a disintegration time of less than 5 minutes. The friability was acceptable in all the cases, and these are the tablets that were obtained for these 3 prototype formulae. Critical challenge that was identified for formulation development and the subsequent interventions that were decided was hygroscopicity, because we have chosen the co-crystal with the malonic acid as the optimal candidate for formulation of the tablets. But we know from our hygroscopicity studies that this co-crystal was much more hygroscopic as compared to the API. Therefore, it was challenging to process this using unit operation involving higher amount of water, such as wet granulation technique. And that is why we had to proceed with alternate manufacturing processes like dry granulation or the direct compression process. This is a general discussion on some of the suggested formulation strategies for overcoming the challenges that are posed by co-crystal during the formulation development. Some of the co-crystals will show very fast transformation to the API, which will be reflected as a spring effect. And in those cases, we will have to delay this conversion of the co-crystal to the API if we have to harness the solubility benefit from that particular co-crystal. This can be done either by using pH modifying agents or using surfactants, using polymers, or a combined approach involving surfactant and polymer. These are targeted at delaying the supersaturation from the co-crystals so that the benefits that we want to obtain from the solubility of the co-crystals can be obtained. For enhancing the dissolution, the particle size reduction can be used as one of the strategy. If permeation is causing the problem, then we may use some of the permeation enhancers, although this is not a very desirable strategy because most of the permeation enhancers will have safety related issues. They are toxic in nature. For improving the chemical stability, pH modifying agents can be used, and for a packaging strategy Looking at developing a drug product from that co-crystal is the safety of the co-former must be ensured right in the beginning, because later on it is going to give problems with the regulatory approval process. This is followed by the pre-formulation profiling of the candidates or the co-crystal candidates that were shortlisted. Rivaroxaban 4-HBA co-crystal was rejected or not taken forward because of poor stability. The co-crystal with the oxalic acid had a rapid transformation to the pure API, which means the solubility advantage was not maintained for biopharmaceutically relevant time frame. It also showed poor stability because we saw certain degradation occurring in these cases. Based on this, the co-crystal was selected as rivaroxaban malonic acid using a weighted criteria matrix. We then developed the formulation using the optimal co-crystal candidate and obtained improved in vivo performance and improved manufacturability. These are the take-home messages from today's presentations. Co-crystals have provided a broad platform for modulation of material properties that are critical during formulation development and have emerged as a promising alternative to traditionally used solid forms like polymorphs, salt forms, and amorphous form. Despite the rising number of research publication and patents, the systematic approach for development of co-crystal based formulation is lacking in the field of co-crystal, and we tried to fill this particular gap with this study that we carried out with rivaroxaban. Translational development of the novel solid form of co-crystals and its conversion from bench to bed may not be a straightforward process due to unique properties and structural features of the co-crystals. As outlined using the case study of rivaroxaban, the suggested pre-formulation based strategy can guide the product development in number of ways. It allows us to choose the suitable co-crystal for further development, helps in identifying potential problems during processing and manufacturing of the formulation, allows understanding of potential stability during the product shelf life, and also helps us in devising alternate strategies for handling, formulation, storage, and manufacturing of the final drug product. Thank you very much for your attention. If you have any questions, I will be happy to answer that. Later on also you can contact me through this email ID akbansal@niper.ac.in. Thank you very much.
Namaste, sir. Namaste, sir. Actually, we have very good session which enlightened us with the latest formulation and these things, and we came to learn about how we are using the co-crystals as a new novel drug dosage form. And actually, during when I am teaching the fourth year B Farm, we came across a new topic, sir. And the new topic is use of platform technologies. And in that, actually, I came across this nano crispy. Actually, now I am remembering that. And this is, I think, this is a new platform for drug delivery, sir. And that we came to know about good knowledge about the directly from the innovator. So I want the participants to ask some questions to our reputed Dr. Bansal Garu, so that you can use that to process further research. Participants, please post your questions in the chat box, or you can directly ask through the.
So as I mentioned, if you have some general questions also which may not be directly related to today's presentation, feel free to ask them also.
Hello, good morning, sir. Am I audible? Dr. Arvind?
Apologies for the technical issues. The questions from the audience will be posted to the speaker directly. Please bear with us for a few seconds. Thank you. Dr. Madhavi BLR would like to ask a question, sir. Bansal, sir. Dr. Madhavi, you can please unmute yourself and ask your question.
Yes, sir. Thank you.
Please go ahead, Dr. Madhavi.
Yeah, sir. Am I audible, Dr. Bansal?
Your voice is not much audible. Can you keep mic closer to your mouth and speak?
Hello, sir. Am I audible now?
Yes, yes. Go ahead with your question, Dr. Madhavi.
Yeah, it's a general one, sir. Thank you for the presentation today. Because as part of the UGE program curriculum, we generally talk about solid dispersions. Right. So does this because earlier this classification and this much of technical detail was not available maybe around a decade ago. Hello.
Hello, yeah, we can hear you.
Yeah. So would you just clarify if this co-crystals would be an extension of the traditional solid dispersions we were talking about? Because there also we talk about a hydrophilic carrier mixed with a polysoluble drug substance.
Okay, so the question is that there is a well-established technology platform called as solid dispersions, and solid dispersions can be further classified into amorphous solid dispersions, nanocrystalline solid dispersions,
Yes.
or microcrystalline solid dispersions. Uh, these classifications are based on the type of the solid form that is present in the solid dispersion for the API.
Correct.
For example, in the case of amorphous solid dispersion, amorphous drug is usually dispersed in a polymeric excipient to obtain certain solubility advantage. In the case of nanocrystalline solid dispersion, nanocrystals of drug are dispersed in polymer or small molecule excipient. Similarly, in the microcrystalline solid dispersion, drug in the micronized form, which will be around say 5 to 10 microns, will be dispersed in the matrix of polymeric excipient or a small molecule excipient. Now these are some of the technology platforms which are used with the existing API. Say, for example, if you have rivaroxaban as the API, you can generate amorphous solid dispersion of rivaroxaban or the other types of solid dispersions. While in the case of co-crystals, what we are doing is we are generating a completely new solid form, wherein in the crystal lattice, both the rivaroxaban and co-former molecules are present. So it becomes a new solid form. It is a crystalline solid form, and then these solid forms can be used for development of the formulation. The advantages from co-crystals are usually again similar to what you get from solid dispersion in terms of enhanced oral bioavailability. But we have to look at it slightly differently, that in the case of co-crystal, we are generating a new crystalline form of the API.
Okay, sir.
Okay, so this is the difference between the two platforms, which are both used for mostly increasing the water solubility.
Water soluble. So would this require any separate regulatory aspects and also like are they treated as new molecular entities or something? The co-crystal?
The co-crystals are not treated as new chemical entities because of the fact that in the crystal lattice, the molecules of API and the co-former are held together by non-covalent interactions like hydrogen bonding, electrostatic interactions, and van der Waal interactions.
Yes.
So after the dissolution of the co-crystal, again the API will become available, and the same API will be responsible for eliciting the
Everything.
pharmacological effect. From a regulatory perspective, US FDA treats co-crystals as a special case of polymorphism. Polymorphism is when a drug is able to exist in two or more crystalline forms. So co-crystals are also taken as a special category of polymorphism.
Wonderful. Okay, sir. Thank you so much, sir. Thank you, organizers.
Yeah, thank you very much, Dr. Madhvi. Sir, Bansal sir, we have one question from Zoom audience. Shall I go ahead with the question, sir?
Yeah, please.
Yeah, the question here is from Dr. P.V. Swami. Can we go for solutions of poorly soluble drugs filled in the soft gelatin capsules? This is the question, sir.
Okay, so whenever we have a poorly water soluble drug, we should first look for couple of pre-formulation parameters, and two very important parameters that we should look for are the melting point and the log p value. Log p value is, as you know, the partition coefficient between water and octanol. So if you know the melting point and the log p value, that will help you in choosing the right type of solubilization technology. There are majorly three technologies which are commercially utilized for poorly soluble drug. First one is amorphous solid dispersion, which Dr. Madhvi was referring to. Second one is nanocrystals, wherein you can reduce the size of the crystal into nanometer size, that is below 1 micron. That will lead to increase in the dissolution rate and solubility. The third technology that is used is called as the lipidic systems. And these lipidic systems are the drug that has been dissolved in a lipid-like excipient, and this is usually in a liquid form, and they can be filled either into a soft gelatin capsule or into a hard gelatin capsules. As you may be aware, these days liquid filled hard gelatin capsules are also available. Now, the criteria for a drug to be suitable for solubilization in the lipid excipients and then filled into a soft gelatin or a hard gelatin capsule would be that it should have a high log P value, which means the drug should be lipophilic. The second criteria is that the melting point of the drug should be low. So if you have a drug candidate whose log P is high but melting point is low, it is a good candidate for lipidic systems like self-emulsifying drug delivery system, which can be then filled into the hard gelatin capsules or soft gelatin capsules. So the solution will not be in water or polar solvents. The solution of the drug is in the lipid-like solvents. I hope the concept is clear. If there is something further, you can ask. Thank you.
Namaste, sir. Actually, we have a very enticing session which provided us with very good knowledge about the co-crystals and how to use new platforms. So actually, we are waiting for again new session from the same speakers like reputed Dr. Bansal Garu. And so I want to propose a vote of thanks. And now our colleague Dr. Nagarjun Reddy sir will give the vote of thanks to Dr. Bansal.
Good morning, sir. Good morning, everyone. First of all, for some technical issues, we are sorry for some technical issues going on here. I will propose my vote of thanks to our beloved speaker. I am Nagarjuna Reddy, working as Associate Professor in Department of Pharmaceutical Drug Regulatory Affairs. I am here to present vote of thanks for today's webinar speaker, Dr. Arvind Kumar Bansal Garu, Professor and Head of Department Pharmaceutics, NIPER, for enlightening us with a good knowledge. It gave deep insights into the topic and also revealed some interesting facts. Dr. Arvind Kumar Bansal Garu told us about co-crystals was really informative section, and it also helps us in out studies and future. From the bottom of the heart, we, the whole fraternity of Sri Vishnu Educational Society and also from Sri Vishnu College of Pharmacy, we thank you, sir, Dr. Arvind Kumar Bansal Garu, in spite of your busy schedule for this event, for presenting a seminar in this event, sir. Once again, thank you, sir. And also, it's our privilege to specially thank our director, sir, Dr. Kumar V.S. Nimani Garu, for his cooperation and also for introducing such a speakers like you, sir. And also, I extend my thanks to our principal, Dr. K.S. Nataraj Garu, for his guidance and also moral support. Last but not least, I convey my thanks to AICTE for providing financial support for this program. Thank you, sir.
So I also thank the organizers for inviting me, and I am happy if the information that I shared today can be used by the participants in their research work and the teaching work. I wish all the best to all the participants and especially to the organizers of this event. Thank you very much.
Thank you, sir.
I thank the participants also for participating in your webinar. And in the afternoon, we will be. Thank you. That's all for today. There is another session after 10 minutes. Thank you.
Dear participants, we appreciate your patience during the technical errors from us. Please do join us at 11:10 a.m. For the next talk of the day. It is the talk by Professor Umesh K. Patil, Professor, Department of Pharmaceutical Sciences, Sagar Central University. The talk is, I hope you will also enjoy the talk. Thank you very much. Please do join us at 11:10 a.m.